I'm going to talk about some exploration of patterns. And just to introduce myself, I studied mathematics in Prague and in Amsterdam. Worked as a researcher, consultant, programmer, and traveled a little bit over the world and played with some machine learning and some smart algorithms. And this is a project that I actually started with a patent lawyer in Hong Kong. Let's do some exploration into patents. Yeah, so people are really innovative from long time ago already. So they are coming with very, very interesting designs. And they are happy to actually profit with them, so they patent them. So these are really like very useful innovations that were patented already like more than 100 years ago. You can still find them in like Google database of patents. Even you can find an artificial snake there, if you look hard. Okay, so this is one way to explore patterns, but I actually looked more at the text side of natural language of how the patterns are described. So the outline of this talk is, first I will start with the motivation behind this project. Then I will describe what Kung Fu is actually needed to deal with this data. Then I will introduce the workflow, how to actually build this semantic space using topic modeling and very, very nice library Gensim. And finally, I will conclude with some, future work, or actually also like current experimentations. So the motivation, why patents? So here you can see the number of granted patents by grant year. And these are the United States patents. So you can see that the space is actually getting quite crowded. And unfortunately, the system is quite broken. It's not dealing with the innovation in the right way. The patents were actually designed or introduced to support innovation, but it seems like nowadays it's actually more suffocating all the innovation. So we should look into this and actually try to do something with it. Also, I would like to know, is there anyone of you who actually filed a patent application who actually has experience with this? And I always love to hear the war stories. Actually, from like engineers that had to deal with the lawyers and all the process. So, the process is not that simple unless you have actually like some buffers in like big company that deals with this, with the lawyers. So it's also slow and costly. So these are the negative reasons why to do this project. The positives are that the data, the United States Patents and Trademarks Office, the data is freely available. They actually release the new data every week. And the data is also structured. And it's mostly consistent. It's actually, the language is consistent over the years. And also it's a great chance to learn something really interesting, some new technologies, and basically explore a new space for your smart algorithms. So data Kung Fu. Kung Fu is a Chinese term, referring to any study, learning, or practice that requires patience, energy, and time to complete. And indeed, dealing with this data requires patience, energy, and time to complete. Because the data is, even though it's structured and the language is consistent, it's not ready to actually process by the natural language processing tools. So how does it actually look like? Currently, the data are provided in XML format, which is nice, but before that, it was in the SGML-like key value store. It was obviously much more difficult to deal with these text files. Also, the data we are actually using at the moment are from 1975 till present. Before that, the patents were purely paper-based. And even though they are scanned and OCR'd, they are not actually very useful. And it takes lots of effort to actually get some useful information from them. For these almost 40 years, the USPTO actually used 8 or probably more than 8 different formats of for this data, for the schema. And so we have to somehow treat it. The data has more than 70 gigabytes, and that's compressed, and that's just text. We are not dealing with pictures yet. So it's not small. And the data consists of patent grants and patent applications. So when I actually checked the data and I was asking how to actually parse this, it's a little bit messy, it's not clear how to actually extract the useful information from that. So I had to actually study all the XML formats and the schemas one by one, and wrote a parser that worked, processed few years of data and then stopped because, the format changed. So I had to do it again and again. And I finally actually got some database, but then I found that there are actually many issues because, for example, the data needs disambiguation. When you have something like one entity like name of company, let's say General Electric, then different lawyers, different people actually input it into the database slightly differently. One can write General Electric Inc., one can write GE, and one can write General Electric Company. And it's the same stuff, but our simple parser actually treats it as something different. So this is actually quite not exactly easy task, this disambiguation. So I had to actually look around what's available, if there is anything. And I was lucky enough to find that there is Coleman Funk Institute for Engineering Leadership at University of California in Berkeley, and they do exactly this. And they wrote a parser that actually does also the disambiguation and basically data preparation. And they released it as an open source software. It's written in Python 2, and it's available on GitHub. So I was very happy to see this. So I can actually replace my parser with this much better one and tweak it for my special use. And the Funk Institute actually is also doing something with the data that they parse. They actually released the patent search tool online, which is actually not very online because you input a query and you give them your email address and they will mail you the results a few days ago, after maybe some time. But it works, and they do lots of descriptive statistics and some nice displays of the data. And it's also based on the Harvard Dataverse network. So that's it. The patent data process flow looks like this. This is actually the Coleman Funk Institute process flow. I'm using parts of it. definitely you have to collect the data and in the XML format, split it into individual patterns, parse the XMLs, fill the relation database, then run the disambiguation algorithms on the processed data. This disambiguation is actually a computationally intensive process, so the code is written in C++, and it takes quite non-trivial time to run it, even on like smaller data. Then, well, from the prepared data, you actually you can run some new statistics on it, and you also do some geocoding, and then you consolidate the data with your old big database of patterns. And then the Funk Institute also provides an API and some visualizations and like connections to their online apps. So the schema of the data that I'm actually using looks like this. Well, you have the patent in the center, and the linkage to the patent is from all the like important parts that are part of the patent, like assignee, application, lawyer, inventor, references, citations, and some special numbers. So, for example, here is the entity relationship diagram for patents with citations, claims, applications, and classes. So this is basically how the relation database looks like. Yeah, for example, yeah, you can do lots of descriptive statistics on this data, and that's exactly what the Funk Institute does. So this is, for example, number of inventors per patent. Well, it seems like most patents actually have one inventor, and it kind of decreases exponentially. If you are interested, you can definitely visit the Funk Institute website, and they provide lots of other information. But I will focus on the semantic analysis, semantic exploration of the textual data. So I do something called topic modeling. I want to actually replace part of the work of the patent lawyers. So the use case is I have a description of some invention, and I would like to find semantically similar documents on the patents that are already in the space. So for that, I actually have to build a topic space of the patents. So I compute the semantic similarity of the documents, and then I will compute actually the similarity of the new document towards the already built space. So the tools I'm using are the NLTK library, which is like the referential natural language processing tool for Python, and Gensim. And Gensim is actually, the design of Gensim is quite different than NLTK, because NLTK is more like a research library that is probably not that easy to use. But Gensim is actually designed for like the real world, for like busy people from business. And so it's easy to use, it's actually very efficient, optimized, and it actually makes this exploration much easier. And the data I'm using are, well, the documents are represented as pure text. Basically, they consist of abstracts, claims, and their descriptions, the descriptions of the inventions in patents. So, but before we actually start the semantic analysis, we have to do some text preprocessing. In particular, something called lemmatization or stemming, and also finding collocations and named entity recognition. So for that, we use Gensim and NLTK. So for lemmatization, which is basically the process of grouping together different inflected forms of a word. So we can actually analyze them as a single item. So it's implemented in Gensim, this function lemmatize that we run on some, well, text or document that is in natural language. And we will get back a vector of, well, non-inflected words. So we can actually treat all the groups of different inflected forms as one word, which is quite useful for the statistical processing. Then the collocations and named entity recognition are basically, we want to detect sequences of words that co-occur more often than would be expected by chance. And also, these words often have like different meaning when they stand together than when we actually have them like split it in parts, because they are like names of companies or like parts of phrases. So for this, we actually use some statistical analysis of the text of the sequences. And it's nicely implemented in NLTK. We find the trigrams and bigrams. So, for example, yeah, when we have the General Electric, we can treat it as a single token, which has definitely business value. And then we also want to remove the so-called stop words, which are generic words such as, well, 6, then be, do, and yeah, we want to remove them because some of these topic modeling algorithms don't deal with them really well. They actually got confused. So again, we use Gensim because, well, stop words are present in Gensim. And before we actually start in the topic modeling itself, we have to deal with the data. Data is big, and we use something called data streaming. We actually heard probably quite something about data streaming and generators and iterators here, so I will repeat again, because it's actually a very useful pattern. We can write this class that takes a file that is too big to fit into RAM and outputs a generator. And we can actually ask the generator to provide the data as much as we can actually deal with. So yeah, it's implemented like this. In this special case, we at the same time also tokenize the text. So we actually split the text into tokens. Just output the list of words. Now we can actually start building the vector space, or like the semantic space. So we do something called vectorization. For that, we have to build library, the dictionary first. And the dictionary is just, we have to index text tokens by integers, because the algorithms don't deal with the text strings so well. They need integers, basically, to index the data. So again, using dictionary in Gensim and inputting our streamed data corpus, we build the ID2 word, which is our dictionary. So basically, it's dictionary of words or text tokens indexed by integers. And then we create a so-called back of words vectors, and also like back of words space. So this is for this we only need a streamed corpus and a dictionary. So let's say we have this text or document, and we tokenize it, and this tokenization, this function actually gives us also the stream of the tokens. We use the doc2bow function on the on the dictionary actually map it into our back of words vector space. And we do this with all the documents that we are processing, so we actually build all the space. And then we finally apply some semantic transformations on this vector space. And well, these transformations are basically some statistical models that model this natural language. And well, basically it only takes one corpus and outputs another corpus. It's just, well, transformation. We have different choices to make. For example, we can choose the latent semantic indexing or latent directly allocation or others. Here I'm choosing the latent directly allocation, but I played with others. Some actually map into like much smaller space, so they can be considered as a dimensionality reduction, sort of. But it's not the case for latent directly allocation. So again, it's nicely implemented in Gensim. You just feed it the corpus, choose the number of topics that you actually want to deal with. Here, from my experience, it doesn't matter how much topics you actually want, because the results are very similar. Unless the number of topics is really small, like single digits, then it's actually influencing the results quite a lot, but otherwise it doesn't matter. And we also feed it the dictionary, a number of passes and some parameter alpha, which I'm not going to talk about. And then we can actually print also like the topics and the most important words for each topic. So, for example, here we can see actually how like the first 4 topics look like in this space. So they are basically just a vector of words with some weights. So actually the topic is actually probabilistic distribution over the fixed vocabulary. And then we can transform actually new documents into our space, because we need it for, well, measuring the distance between the topics or the documents. So again, we take the text, we transform it into the back of word space, as we've already seen, by tokenizing it and applying the dictionary function. Next, we transform the text into the LDA space, into the topic space. So we've already built the model. So we apply the model on this back of words vector, and we get another vector that is in our LDA space. And then we can, for example, find the document's most significant LDA topic by using this print topic function on the model and feeding it the index of the topic that we find by finding the maximum from these significances of these topics in the vector. And now we would like to also like evaluate how well it actually how good the model is. But it's quite tricky because the topic modeling is unsupervised task. So the best we can actually do probably is we have to evaluate it on the task we want to actually model. So our goal is to retrieve semantically similar documents. Therefore, we actually manually tag similar documents, okay, group them together, and then compare what actually the semantic model gives us back, if it actually can map the documents together or not. But this is quite resource intensive. I mean, human resource intensive. You have to actually, well, manually prepare the documents and then check them. So people came out with different methods that are easier to do for people. For example, the word intrusion. which is basically done like that. When we have a train topic, we take the first 10 words in the topic, like sorted by the significance for the topic, and we substitute one of them with a randomly chosen word, which is the intruder, and then let a human detect the intruder. So this actually works quite well, because people are quite good at detecting these intruders if the topic is kind of clear. And we can actually also like completely avoid the human intervention, the evaluation. And this method actually works like this. We split the documents into 2 parts and then only check that the topics of the first half are similar to the topics of the second half of the same document, and also that the halves of different documents are mostly not similar. So as I've said, the topic is a distribution over a fixed vocabulary of terms, and the general idea behind the latent Dirichlet allocation is to statistically model documents as containing multiple hidden semantic topics. So let's explore the topics in the topic space. So here we can see actually 6 most significant words of 4 random topics. And well, as you can see, it's actually not very, it doesn't say us much. I mean, you cannot, it seems like you cannot use it for that, like in your decisions or like your search, because these topics, it doesn't make that much sense. So it seems like it's much better to actually measure the topic distance between different documents and just ignore the topics. So here is the result of running this topic modeling on this pattern data. And as you can see, this is a plot of topics as they appear in documents. And you can see that even though there are many topics, well, in this case we chosen like 100 topics, each document contains only few of them. Just most documents actually contain between 10 and 25 topics. So it's a sparse model. So we can probably, maybe we could use, for measuring this distance between topics, use some, NumPy functions or SciPy functions for basically matrix computations. So let's try to compute the semantic distance queries by using the distance or pdist function on the matrix of the topics. So if we actually try to compute the pairwise distance of all this data of these topics, we get memory error because it's just too big to fit into memory. So again, we have to seek help from Gensim and the class similarity, which does something called document indexing. So it builds index of our documents based on their semantic similarity. We feed it our corpus of the stream data, and we say how many features we want. Basically, this number of features is probably like, in this case, it's the number of topics we want to deal with. And this similarity class splits the index into several smaller sub-indexes, so it scales really well. It's memory efficient. And now, when we have actually computed the index, the similarities, we can query, new text and ask for the similarities or for the most similar documents in the space. So again, we vectorize the text into backward, then we again transform it into our LDA space, And by using the index and telling the index how many documents we actually want to see, we query the index for our vector in the LDA space. And we get back the indexes and, well, basically the ranking of the documents back from the index. So we've actually built the topic space, which we can now ask for the similarities. And I would like to just conclude with some current experiments that we are running, and we would like to plug in to this, well, search engine or recommendation engine later. One of them is the Neo4j, the graph database, because, well, these patterns actually have this graph structure. That's because each patent actually have some references and links to other documents. So we could actually take advantage of it and plug it into graph database. And Neo4j, for example, has so nice features of displaying the graph data into browser. So this is definitely something we are working on. And also Elasticsearch. We've used Elasticsearch for indexing our documents and using it for the full text search. But we still would like to explore more of what analytics is possible to do with the Elasticsearch and how to actually incorporate more the full text search and semantic search and the recommendations. So basically, we want to build the whole recommendation engine for, well, improving applications for patents. And, well, and then in the more distant future, we could actually also do the drawings analysis or the picture analysis. Can actually deploy some well, image analysis algorithms that can actually recognize very similar real-world innovations. And what's actually interesting is the blockchain or the decentralized protocols. For example, the Bitcoin blockchain. It doesn't have to be necessarily used for monetary transactions. It can be actually used for so-called smart contracts. So you can actually automatically create contracts in this public logbook, and based on that you can actually create market that would be ready for machine use. And from that we could finally create the artificial patent lawyer, hopefully. So, thank you.
So you mentioned that sometimes some of the topics don't make sense. Did you try to force some topics into the system, like giving the information that some topic is actually interesting?
No. I actually use it basically in the way it helps me to cluster different documents into, well, basically clusters based on the similarity of the topics, which seem to be actually more useful because you get, I mean, the patent lawyers are actually forcing these topics when they file these patents according to some classification. But what's actually useful, or seems like to be more useful, is to actually use the unsupervised algorithms to classify the documents according to underlying text. So that seemed to be more useful. Yeah.
So the final goal is to get rid of lawyers.
Yeah, in the first instance, we have to collaborate with the lawyers because they have to actually tell us how they work and what they do. So after that, we can replicate them. And it's actually possible that if we actually take it into extremes, the system actually might collapse because there might appear some inconsistencies in how the data are actually dealt with. So you can get some contradictions in the pattern space. So I would like to actually see this, if how it will progress.
So at the beginning you talked about collocations to discover bigrams and trigrams. In most of the results you showed, it looked like it was unigrams you were putting out. Can you say a little bit about the value you found in bigrams and trigrams versus just raw unigrams?
Oh yes, you are right. You are right. Yeah, I use those like simple examples, and yeah, so all these tokens were actually single words. But in practice, when you deal with this real-world text that are basically produced by some companies, then these companies have often names that are composed of more than one word. So it has actually real business value to treat them as one entity, because it has much more significance for this invention or the document than when you actually split it into like two words that have some meaning in the natural language, but it's completely different from like the collocation of the words.
I've spent a lot of time working on client problems around disambiguation of named entities to merge different spellings of the same company, General Electric, GE. What kind of approaches are you using to merge entities together? I have not tackled that problem yet. Do you treat General Dash Electric and General Space Electric and GE and G.E. as four separate entities, or they will merge into the same company entity?
You mean, you are asking more, I think, about the process of disambiguation. So, yeah, as I mentioned, that's actually done by the Funk Institute in their disambiguator. Because, yeah, I'm actually already getting the disambiguated data, which is much nicer to deal with than without it, for this reason. Because you actually get meaningful, numbers or statistics. When you run the statistics on the data, then it's definitely useful to treat General Electric as one company, not like the 10 different companies. And yeah, so it's the C++ code that is on GitHub that you can check if you are interested. Yeah, so it seems there are no more questions. There.
I was wondering, you have data on collected patents. Could you do the same kind of analysis on scientific journal articles and see if they actually give some correlations for patents and maybe prior art in science, or whether science triggers patent applications? I wonder.
Definitely, there was research going on into semantic exploration of scientific journals or scientific articles. I'm not aware of if anyone actually tried to find correlations between these scientific articles and patents, but there are definitely some, obviously. But I personally don't know about this. So, any more questions? Yeah, so thanks.